Okay, this is section 13.2, and this is example 4. And at the top of this page in your notes, you have a few properties of line integrals, and it's important just to know that the path matters in regard to the line integral. And so, anyway, we'll use those off and on. Okay, example 4. So we have the line integral of sine of x dx plus cosine y dy, and c is the half circle from from 1, 0 to negative 1, 0. So that's going to be a half circle that looks something like this, and the path is going to go like that. And then we're going to go from that point, negative 1, 0, and go to negative 2, 3 in the path of a line segment. So a little bit off scale here, but that's okay. So we have negative 2, 3. All right, so we're going to do this in two different parts. We talked about this before, how we'll need to split this one up. So for our first one, it would probably make sense to parameterize it and use our circle technique, cosine t and then sine t. And r prime, the derivative of this function, would be negative sine t and then cosine t. And the original integral is in terms of x and y, but probably makes a lot of sense just to put this all in terms of t. So our integral then would be from 0 to pi based on the path we're taking. Again, that's in terms of t. And then x is going to be cosine t, and y is going to be sine t. So we have, in our integral, we have sine of, instead of x, we're going to have cosine of t. Now dx is going to be the derivative, and the derivative, I'm going to write this off to the side here. So if we take dx dt, so the derivative of cosine t, we get negative sine t, which we had written for r prime. But remember, we need to solve for dx so that we can do a full substitution. So what we get is dx, which is equal to negative sine t dt. And then what we're going to have is cosine of y, and y is sine of t. And then dy in a similar way is going to be cosine t times dt. All right, let's go ahead and simplify this down. We're going to use a u substitution. So let's use, actually we're going to do two u substitutions. Let's do a u substitution cosine t, and du will equal negative sine t dt, which you can see is already there. And then just to try not to be too confused here, let's do a v substitution for this other one. So we'll let sine of t be v, and then dv is cosine t dt, and that's going to be there. So what we get, and I'm not going to do anything with the limits right now, what we're going to get here is the integral of sine of u du plus the integral of cosine v dv. And we're just going to do these separately because we can just integrate each piece. So the antiderivative of our first one is going to be negative cosine of u, and then we have sine of v. And if we turn this back in terms of t, this is cosine of cosine t plus sine of sine t. And then we're going to evaluate this from 0 to pi. And so what we get is negative cosine of negative 1 plus sine of 0 subtracted by negative cosine of 1 plus sine of 0. Now, if you remember, we were doing an example earlier where we dealt with sine, and sine is a odd function, and so sine of negative 1 is equal to negative sine of positive 1. Well, cosine is even, and so cosine of negative 1 is equal to cosine of positive 1. So this actually simplifies to negative cosine of 1. sine of 0 is 0, and then we have plus cosine of positive 1, and sine of 0 is 0. And it's not too satisfying, but we get 0 out of this. So when we're looking at our original, that red path that we're taking along this curve, that line integral is equal to 0. So now what we have to do is take a look at the blue path. And again, in our original line integrals in terms of x and y, but because of the trigonometry that we have, I think it's probably easier if we just convert everything to terms of t. So when we look at the next path, the blue path, let's come up with a parameter equation of t using our line technique. We had done that a couple examples ago. We're going to go from -1, 0 to -2, 3. So the vector that is formed by that is going to be -2 minus 1, so -1, and 3 minus 0, so 3. And then we should use the point that we start at, which is -1, 0. So again, our formation of a line in parameter form looks like this. So x is going to be equal to -1 minus 1 times t, and y will be 0 plus 3 times t, and we could make y just equal to 3t. If we have each of these parameters, then dx will equal -dt, and dy will equal 3 dt. So again, we need our differentials so that when we come up with our line integral and change it all to be in terms of t, we're set to go. So again, here's our original. So the line integral of sine of x dx plus cosine y dy. And we're going to convert this into the integral. Now remember, because of the vector that we found here, and because of the point, we have a t minimum of 0 and a t maximum of 1. And again, this all goes back to when we did lines and segments in chapter 9, and we did it again in 10. So t is going to go from 0 to 1. Then we have sine of x, which is -1 minus t, dx. So again, I'm doing a substitution here. So we have sine of x. Since x is -1 minus t, I put it in. Then we have dx, and remember dx is negative dt. Then we have cosine of y, and y is 3t, and dy is 3 dt. Okay, if we're going to do the antiderivative, actually first let's simplify. So we have 0 to 1 of negative sine of -1 minus t plus 3 cosine of 3t, and all of this has an operator of dt. All right, so let's do our antiderivative. So we have negative cosine of 1 minus, -1 minus t plus sine of 3t. Those are technically U substitutions, but I think we can maybe get through that without doing a full U sub. This gives us negative cosine of -2 plus sine of 3 minus negative cosine of -1, and then sine of 0. Okay, and then that simplifies to, let's see, since cosine's even, that's going to be negative cosine of 2, and we have sine of 3, can't do much with that stuff, and then we have cosine of -1, which is the same thing as cosine of 1. And that's about it. We had that other path, but that had a value of 0, so this happens to be our final answer then. Okay, the next video will be on example 5.